Hi, everyone. Welcome to our second edition of the virtual Astronomy on Tap. We're live. I am Carbon Queen.
And I am MCM33.
What are you drinking tonight, MCM33?
Well, while I am repping a Dallas brewery, I am in fact drinking a beer from a Houston brewery, Hop Tongue out of Orbach.
Still Texas, that's awesome. I ran out of beer and wine this week, and so I made a pisco sour instead with some Chilean pisco I brought back.
Ooh.
And I'm very fancy.
Perks of being able to go to South America to observe.
Very true. Yes, there's an unobserving run. All right, let's get started. So welcome again to Astronomy on Tap Live. Everything's awesome. Just in case you didn't see the last one, we actually are still doing trivia. So follow this link, tx.ag/AoT trivia, to get access to our trivia. And the winners will be emailed. You have to get everything right to be one of the winners. And always like and subscribe to our YouTube channel. You'll be notified if you subscribe to every time we go live or any new videos we post. We're going to try and keep you all engaged as much as we can during these uncertain times. And then also follow us on the other social medias. You know, we have Twitter, we have Instagram, Facebook. We also can check the host of events that are available under the overarching umbrella of astronomyontap.org, which is all the Astronomy on Taps and all their events attached to it. And then also, we normally, when we have our actual in-person Astronomy on Taps, we have it at the Grand Stafford, which is this amazing theater, this really awesome historical venue. The staff at the Grand Stafford are amazing. And so we want to help support them during this time when they're not able to have revenue or income. And so if you want to tip your bartenders virtually, use this Venmo link, Jose Quintana 20, and just put Stafford Tip in the description and the money will go to them. And they'll know that it comes from our AoT tips.
Tip your bartender.
Tip your bartender. And then also, if you want to help support Astronomy on Tap BCS, feel free to help support us as well. And so we have two different donation options here. We have Venmo and also this other Cash App, which is not familiar. But our tag on both of them is AoT BCS. And we actually have some Astronomy on Tap shirts left over with the logo on the left-hand side, as you can see. And those are for a donation of $15. You could potentially get one if you want. We'll figure out how to get it to you. And then finally, or next to last, our next event is June 17th. It's, again, the third Wednesday of every month. And so keep tuned for that. I think I'll be speaking at that one. It'll be fun. And then finally, put your questions in the live chat. So we'll have a live chat going, and hopefully you're already engaging in it. Through this entire live stream, we have moderators checking the chat, and they'll be compiling questions during each of the talks that we'll be able to ask the speakers at the end of their talks. And so don't wait, just do it as soon as you think of the question. Otherwise you might forget, and we're gonna have a great time. All right, so without further ado.
All right, our first speaker is going to be Jasleen Matharu, who is a postdoc in the astronomy department, and she arrived in College Station, it can't be close to a year ago, but it was definitely last year. Jump in, correct me, please. So Jasleen, before we dive into your talk, what did you want to be when you grew up? Was it always an astronomer?
Oh, wow. That's an easy question. Yeah, my story is a sad one. I always wanted to be an astronomer since the age of 11. So I'm living the dream.
Hey. All right, without further ado, Jasleen.
Right, let's see if I can start this sharing. Right, so I hope you can see all that. Today I'm a researcher at A&M, and I actually work on galaxies, but today I'm not going to talk about that. Today I'm going to talk about something that I think is just as important and is actually something that gets a lot of people into astronomy in the first instance anyway. And that's actually a change in perspective on looking at things in astronomy. So for me, it was when I was about the age of 10 and I looked at the moon through a telescope for the first time. And up until then, I thought I knew everything about the moon because I saw it in the sky every night. I knew the size of it, I knew the color of it. And I thought, wow, the moon's kind of boring. I know everything about it. But when I looked at it through a telescope, I realized, wow, there's a lot of detail here that I'd never seen before. And all that came into my head was just a whole host of questions that I wanted to answer. And that's kind of what I want to illustrate on this slide here. This is a montage of images that was taken actually only a month ago by the spacecraft Bepi Colombo, which is a mission to Mercury. And it actually shows the Earth there, you can see in the left-hand side. And if you really squint, I'm going to pause the video here and just forward it. Near the solar array on the right, you might see this tiny little dot, and that's actually the moon. And this really blew me away because this is looking at the Earth and the Moon system in a completely different way. Like, you can't really gauge the distance between the Earth and the Moon when you're on the surface of the Earth. And it really shows you how small the Moon is relative to the Earth. And for me, this is breathtaking. And so this talk is really about looking at where we are in the universe relative to everything else that we know that is in the universe, all different astronomical bodies. And along the way, I'm going to try and add in some recent developments in science that have made this possible. So let's start very easy. This is planet Earth. This is where we all live. Most of us who are at least talking or organizing this event are about here in Texas. And if we were to take the moon and put the moon on this slide and ask ourselves, how big is the moon relative to the Earth? Well, the moon would be about this big. The moon is 30% the size of Earth's diameter. So that's quite small if you think about it. But if you look at the whole solar system, it's actually one of the largest satellite to planet ratios. In fact, it is the largest. The next largest is between Neptune and Triton, which is a moon of Neptune. And I kind of gave this away in the first slide, but if you were to take the Earth-Moon distance and shrink it to the size of this slide, this is actually the correct distance. And that is the correct relative size of the Earth and the Moon. The Earth and the Moon are over 300,000 kilometers apart. And with the help of telescopes and space probes, we have been able to understand what the solar system actually looks like. And this shows the correct relative sizes of the planets to the sun. When you look in a textbook, this is usually what the solar system looks like. You have the planets in a row and the sun off to one side. And I'm sure all of you, or many of you, may have know the ordering of the planets or were forced to learn some weird mnemonic to remember the order of the planets. You might notice that Pluto is not in this image, and that is because Pluto got downgraded in 2006. I know many people are sad about this, but it's basically because Pluto hasn't managed to clear its orbit of other astronomical bodies. So it shares its orbit with other large objects. So we've had to downgrade poor Pluto to a dwarf planet. So the next thing I'm going to talk about is Mars. And the reason I'm going to talk about Mars is because it's actually the most similar planet to Earth in our solar system. And this is actually shown in the animation on the right-hand side, where you can see that the Earth and Mars actually have a very similar rotational period and tilt to their rotational axes. This means that seasons are comparable between the two planets. And this makes Mars very interesting to us because it's similar. So we want to know more about it. And we've managed to send a lot of unmanned missions to Mars to understand more about its history, its composition. NASA has sent 4 rovers to Mars, and it's planning to send a 5th in July, I guess COVID-19 pending. The most recent, the most recent rover that is on the surface of Mars is the Curiosity rover. And this is a real image. It's a selfie that the Curiosity rover took in 2015. And this is a real image of the surface of Mars. So, I mean, you could argue it looks a lot like Earth. And since about May 2020, it's been on the surface of Mars for nearly 3,000 days, which is a long time. Again, this image, now I find this image really interesting because it's really easy to mistake this for Earth. Like, especially if you look at the layers in the rock, this is what's really astounding, is that it shows that in the early history of Mars, there was clearly exposure to water that gives you these layers in the rock, which is really amazing to see. We've also been able to fly missions to the outer planets and take imaging with exquisite detail. So this is Jupiter. zoomed in. And you can see the huge storm on the right, which is the famous red spot. And it's been observed since the 1800s. So this storm has actually been around for 200 years. Now, you might want to ask yourself, where are we relative to Jupiter? How big are we? Well, actually, if we were to put the Earth on this slide, the Earth is about the size of the red spot. That's huge. Like, it really gives you a sense of scale of how big Jupiter is. Jupiter's diameter is 11 times that of the Earth, and you could fit over 1,000 Earths within Jupiter. This is actually an old image of Jupiter. We now actually have much nicer images of Jupiter, and this is from Juno, which was a space probe that was launched in 2011 and arrived at Jupiter in July 2016. And its main aim was to basically find out more about Jupiter, its composition. Does it have a rocky core? Does it have water in its atmosphere? What is the mass distribution of Jupiter? And you can see this is Jupiter's northern hemisphere. You can see it's very stormy, but it didn't stop there. It took exquisite, detailed images of the surface of Jupiter. Here you can see swirling cloud belts and tumultuous vortices. And my personal favorite is this image of the south pole of Jupiter. You may be able to see these sort of blue circles in the center of the image. And those are actually cyclones. These are storms, and you're seeing these over 50,000 kilometers from the surface of Jupiter. So these are actually 600 miles across. Like, imagine a storm that is 600 miles across in diameter. It's just mind-blowing. So we've sort of traveled in the solar system a bit, but now to sort of zoom out and think about the solar system and the system. How big is the solar system? Well, this is actually an incorrect image of the solar system, but it is like what the planets do. They orbit around the sun in a counterclockwise direction, but this image is not to scale. And any image of the solar system you see will not be to scale, because if you were to try and make a model of the solar system that is to scale, especially on this screen, you would have to shrink the planets to microscopic dots. And just to put this in a bit more context, is if you wanted to create a model of the solar system and your Earth was the size of a marble, you would need 7 miles of space to fit your model solar system in. The solar system is huge. Now I'm going to move on to my personal favorite fact of the solar system. And I think this is my personal favorite because I think it's just sheer coincidence. And I haven't been able to find a reason for why this is the case, is that if you wanted, you could fit all the planets within the distance between the Earth and the Moon, and you'd still have about over 4,000 kilometers of space left. So if astronomers are feeling to bring Pluto back into the club, we could actually fit Pluto in. So something to consider. And so now we've spoken about planets. Now the next thing we want to look at is stars. So obviously, let's start with our favorite, which is our star, which is the sun. It's 150 million miles away from, 150 million kilometers away from the Earth. And my favorite fact about the sun is that it takes about 8 minutes for light to travel from the sun to Earth, which means whenever you're looking at the sun, please don't look at the sun like directly, but whenever you're looking at the sun in a safe manner, you're actually looking at the sun as it looked 8 minutes ago, not as it looks immediately. So when you look up at the night sky and you see all these nice, pretty, bright dots, all of these are stars within our own galaxy. And you might ask the question now that we have planets around our own star, the sun. Are there planets around other stars? And have we been able to discover anything about them? And how many are there? What are they like? In 2009, NASA launched the Kepler spacecraft, which was designed to search for planets outside our solar system, but using something called a transit method. And this is a method whereby when a planet moves in front of its star, the brightness that we measure from that star reduces by some small amount. And from this reduction in brightness, we can actually tell certain properties about that planet, as well as detecting the fact that a planet passed in front of the star. So it tried to do this, and it stared at tens of thousands of stars, trying to look for these dips in brightness. And I wonder if you guys can guess how many planets it discovered. Please comment in the YouTube or whatever. But it was astounding what Kepler found, because this is an animation that will show you the array of stuff Kepler found. And these are all the different planetary systems that were discovered. And the solar system is shown as the dashed circles. And we're going to zoom out so you can see the sheer variety of all the planets. You can see they're all different sizes. They're all different temperatures shown by the color bar. Amazing variety. And actually, Kepler found over 1,000 exoplanets. And as of today, we have discovered more than 4,000 so-called exoplanets. And we're actually discovering more than one per day, which is amazing. So the next thing is, we've thought about other stars, and we've thought about how many planets there are out there. The next thing to ask ourselves is, if we have stars, how big are stars relative to what we've learned so far? So rather than me doing the talking here, this video is going to basically give you an idea of how big stars are relative to planets. And we're going to start with looking at the planets in our own solar system, and then we're going to jump to some famous stars in our galaxy. So you can see we've got to the gas giants here. Saturn and Jupiter are some of the biggest planets in our solar system. And now we're going to jump to stars. You can see the huge jump in size. Sirius A is actually the brightest star in our night sky, and Pollux is the closest giant star to the sun. And these are some of the brightest stars we see in our sky. So we're still going larger and larger. This star is actually one of the most luminous in the Milky Way. And now we're actually going to go to one of the largest stars we know of, and ask ourselves the question again: how big is the Earth relative to this star? And that's the size of Earth. So it really puts things into perspective, how small we are relative to stars out there. So we're not going to stop there. We've got to stars now. We've got a good idea of stars. We're going to move on to our own galaxy, which is shown nicely in this image. So if you are lucky enough to live in an area with not that much light pollution, and you look up into the sky, you might notice this very bright band going across the sky. And that's actually our own galaxy. That's the Milky Way. And this image is not a real image of our galaxy. This is an artist's impression of what our galaxy would look like. And we reside about here in the Milky Way galaxy. Now, if we were to draw a circle around all the stars we can see by eye, this would be the size of that circle. Now, to put this into perspective, you can probably see like how small that circle is relative to the Milky Way, but it's equivalent to the size of a coin relative to the size of Europe. So we're talking tiny compared to our galaxy. Our neighboring galaxy, or the closest galaxy to us, is the Andromeda galaxy. And in 4 billion years, we're going to actually collide with Andromeda. This is a video that shows, basically zooms in an image that was taken by the Hubble Space Telescope. And it is one of, I think it is the largest image taken by the Hubble Space Telescope. And if you were to try and look at this entire image, because it's so big, you'd need 600 HD televisions to be able to display this image in one go. So we're just going to start this video, and we're going to zoom into this area. And I'm just going to forward this video and just show you every single dot you see in this video is either star clusters or individual stars in Andromeda. And what I really wanted to show here is you can see the diversity in colors all the different types of stars that reside in one quarter, even the area of the galaxy. So this really shows you how many different types of stars there are out there. And we have only touched the surface in this talk of what types of stars there are. So as I said, poor Andromeda and Milky Way are going to collide one day. And this is what that collision might look like. But you don't need to worry because the stars are sufficiently apart that you're not going to get hurt. And plus, you won't be around to see it. So no need to panic if you are already. So when this happens, the Milky Way and Andromeda are actually spiral galaxies. So they have this really nice spiral structure. And when they collide, they're going to end up looking more like one of these galaxies where you can't see any features in the galaxy. And now the question is, well, we know about our neighborhood, but how many galaxies are there really? Do we know how many galaxies there are in the universe? And one way to think about this is if you take the moon or the area the moon covers on the sky and you tell yourself, let me shrink this, let me draw a circle 1/10 the size of the moon on the sky. And how many galaxies do you think we're going to see in that tiny little area? Go wild with your guesses and we'll see if you're right, I guess. So if we take this area and we zoom in, this is a real image. This is called the Hubble Extreme Deep Field. It was taken by the Hubble Space Telescope and it was released in 2012. And it took over 23 days of time to stare at this patch of the sky constantly to gather as much light as possible to see how many galaxies are in this patch of the sky. And in this image, every single speck of light, apart from some of the obvious stars where you have this nice sort of star pattern with the spikes, every single dot in this image is a galaxy. There are over 5,500 galaxies in this image alone. And some of the oldest galaxies you can see in this image, you're seeing them as they looked 13.2 billion years ago. And this particular age might sound familiar because it's actually very close to what we think the age of the universe is, which is 13.7 billion years. So we're seeing these galaxies as they looked only 500 million years after the Big Bang. Some of the faintest galaxies in this image are only 1/10 the brightness of what you can see with your own eye. So now I think it's probably blown a few people's minds, and I'm sorry about that, but we're going to go even one more step further, which is one last thing. In every single galaxy, there is a supermassive black hole at the center, and they can be detected in various ways. But you know, we've been able to progress a lot in our understanding of black holes. One way you can actually try and detect whether a black hole is there or not is to be able to look at the orbits of stars. And if they happen to be orbiting something that you can't see, that's probably a big telltale sign that it's a black hole. And also actually from studying the orbit, so this is actually a real animation of the center of our own galaxy. These are the real orbits of those stars. What we can do is from the orbits, we can infer what the mass of that black hole is. So here is this video actually shows the real orbits of the stars. And if we zoom in, you can see these are the stars right at the center of our galaxy. But they seem to be orbiting something that we can't see. So that's a huge telltale sign that there is a black hole there. And our own black hole in the center of our own galaxy is 4 million solar masses in mass. But we can go one step further now. We actually have simulations of black holes and what they may look like. So this is a simulation of a black hole. And you can see that there's this material around the black hole, this orange material, and this is actually matter that has been collected in a hot accretion disk. So this simulation is going to rotate in this fashion all the way around, so you can see the whole model. And if you look closely, nearest to the black hole, the material is moving faster than the outskirts. And you can see all these stretches and shears in the orbits because of the black hole's intense gravitational field. You might also notice that when you are looking at the black hole edge on one side, the material coming towards you actually looks brighter than when it's moving away from you. And this is, again, an effect of the strong gravitational field. But we don't so the orange stuff is the hot glowing gas in this black hole. But now, we have gone one step further and we've actually been able to see what a real black hole looks like. So this is a video trying to give you the perspective of where this black hole is. So now we're going to zoom into the sky, into a galaxy called AoT-7. So this is a real image of the silhouette of a black hole, as we call it, because you can't actually image a black hole. Light can't escape it, so you won't be able to see it. And what you might realize is actually, you could almost mistake this for a blurred image of the simulation I showed you. And I think that's one of the most amazing things about this is what we predicted in terms of what we think a black hole will look like. Our observations are starting to look like that. And this orange stuff you see is the hot glowing gas that's falling into the black hole. But just to put this into perspective, to be able to image this black hole, we actually needed a telescope with an aperture the size of the diameter of our own planet. So that's what it took to take this image. And again, to put this in perspective, it's equivalent to trying to image an orange on the surface of the moon from the surface of Earth. Like, this is a very difficult task to do. And so there's one remaining thing to finish this picture and our journey through the universe and trying to understand our place in the universe is, well, how massive are supermassive black holes? And this video will try and answer that using the sun as a unit. And so please guess how big you think, or how massive you think a black hole is in the YouTube channel. But I can tell you now, we're still not finished. Yep, we're still not finished. Yeah, so black holes are really, really massive. They range from hundreds to thousands to billions of solar masses. And this is huge. Like, this is just in the units of the sun. So that's been like our journey through the universe. And I hope that's given you some alternative perspectives of where we are in the universe. How important that position is for you to decide. But I hope you enjoyed it. And I'm happy to take any questions you have now.
All right. Thank you, Jasleen. That was really cool.
No worries.
Aside from a tiff between the Pluto lovers and the Pluto haters, there were also some questions in the chat. The first one comes from Paulina Delgado. What would the Earth look like if we were taking images from stars?
Oh, wow. Well, it depends which stars. I think it would be really tiny, first of all. It depends. If we're talking about a star really far away, the Earth will look really tiny. It might just be a dot. So that's something to think about. Like, for example, the first image I showed, which showed the Earth and the moon, and that was, not as far away as the nearest star. So you can imagine that the Earth would probably be a dot, even, yeah.
All right. Next question, also from Paulina Delgado. What happens if someone comes near a star?
Oh, that's not a good idea. Yeah. I don't think you'd live long enough to know what happened, really. You'd be fried. Don't do that. Yeah, just please don't do that.
We'll do that. Okay. Yeah. This next question comes from Snoop Jedi. How does dark matter factor into our place in the universe?
Oh, that's a cool question. So dark matter is an interesting one because its discovery was by looking at galaxies. So we actually tried to see how stars are rotating in galaxies, and that didn't quite follow what we expected. There seems to be, when we look at how the stars are moving in a galaxy, they seem to be moving, I believe it's slower on the outskirts or not to what we expected. And for that, we need to explain that discrepancy, we need to add more matter there to understand how how galaxies rotate. So that's how dark matter fits in. It fits in more with our understanding of galaxies.
All right. I don't believe there are any more questions. So thanks again, Jasleen, for a really great talk. Okay, so if anyone would like to participate in our trivia, we are still doing that. We will contact the winners by email and somehow get you your prizes. The link is in the description below, along with links to donate to us and our usual venue, the Grand Stafford. Please tip your bartenders. And yeah.
All right. So next up, we have a segment called What's Up with the Cosmic Kid, where we'll learn about what's up in the sky this month and what we could expect to see. So take it away, Cosmic Kid.
Hello, everybody. Who's ready to learn about what the cool things are to look in space? So what's up this month, the May 2020 edition? We've got first what I like to call the easy targets to observe. We've got Mercury and Venus, which are going to get real close to each other. This is going to actually happen tomorrow, May 21st. If you look northwest just after sunset, Mercury will be about 1 finger width below Venus. And Venus will actually be about 30 times brighter than Mercury, even though Mercury is going to be at a full phase and Venus will only be a slight sliver. So that's going to be a really fun target to look. You don't even need any fancy gear to see it. You can just look out with your eyes just after sunset, pretty much anywhere. You can see them pretty easily. Next up, we have the medium difficulty things to look up in the sky. So there's this cool thing happening on the May 28th. You're gonna have to wake up pretty early. It's gonna happen around 4 in the morning. But you can see the shadows of Europa and Ganymede, 2 of the Galilean moons of Jupiter, pass over Jupiter. Everything's gonna line just in the right way where you can see their shadows as they transit over Jupiter. For this, you're gonna want to go out to a pretty dark site, and you're going to want to get some pretty good binoculars or a small telescope to see this, which is why I label this as in medium difficulty. But Jupiter is a pretty common target, and it's pretty easy to spot because it's pretty bright in the morning sky. Finally, I'm going to go over what's called the hard mode targets. So this is going to require a little more trekking on your part and maybe a little bit better gear on your part. There's a supernova that was just discovered last month in the galaxy NGC 3643, which is located in the southern part of the Leo constellation. Recently, it's reached its peak brightness, outshining the galaxy core, making it a really easy target to find if you know where to look. You're going to want a decent-sized telescope to do this. You're going to want a dark site to view it, but it is possible to view the supernova. And I recommend, if you're going to do it, you do it soon, because supernovas will dim over time, and in a few months, you won't be able to see it anymore. In fact, you can see in this picture, right in the center, you might be able to see the crosshairs. The really dark dot is the supernova. The fuzzy patch next to it is the host galaxy that it's in. So you can tell that it's way, way, way brighter than its host galaxy. And so that's a really fun target to look at if you're able to check out your dark site and you have the right gear. And that, my friends, is what's up.
Thanks, Yaswant. Those of you who have been regulars at Astronomy and Tap BCS know that we typically do 2 talks, but this month we have a bonus talk for you. This is coming from Jacqueline Antwidanso, who is a graduate student from Ghana in her 3rd year at Texas A&M, and she recently had a paper come out which is a huge deal. And I'm going to give you a smaller cheer than that merits because I don't want to blow out everyone's speakers. Yay!
Yay!
So take it away, Jacqueline.
Thank you, MC33. All right, so I'm going to be talking about this paper, which was recently published. And before I get into the details, I want to give some context about the leading arm and why we even care about how far away it is. So the surroundings of galaxies are rife with all kinds of activity. This is because the atoms in the universe are moving into, out, and around galaxies on timescales of billions of years. This simulation shows the formation of a Milky Way-like galaxy from 13 billion years ago till the present day. And the galaxy accretes most of its gas from the intergalactic medium, or the gas between galaxies. But there's also gas that is being accreted from smaller galaxies or satellite galaxies, as well as gas that is being kicked out due to energetic activity like supernova explosions, and then being recycled back into the disk. So there's a lot going on. And the gas that surrounds galaxies is called the circumgalactic medium, or the CGM. The CGM is made up of both neutral and ionized gas. Now, stars are formed from clouds of gas and dust. And over the years, we have learned through observations and more recently through high resolution simulations like these, that the CGM is a source of the galaxy's star formation fuel, the venue for gas recycling, like I described before, and most likely the key regulator for a galaxy's gas supply. So this graphic here summarizes the processes that I showed before in the simulation. So the recycling of gas, the accretion of gas from satellites, and processes like that. And because the CGM of the galaxy is where this gas cycle takes place, understanding the CGM is the key to answering questions like, how do galaxies sustain their star formation? What causes galaxies to quench their star formation? Now, the gas in the CGM is very faint. And so one of the best places to study the CGM of galaxies in general is in our own backyard, the Milky Way galaxy. So this is a map showing the gas in the Milky Way CGM. These gas clouds are called high velocity clouds, and they are so named because they are moving at much higher velocities than the velocities of the gas within the disk of the Milky Way, hence the name high velocity clouds. So in order to understand the galaxy CGM, so the CGM of the Milky Way, we need accurate measurements of the physical properties of these high velocity clouds, and in particular, accurate measurements of their distances. And this is because many of their physical properties, or rather how we derive some of these properties, such as their mass, their size, their pressure, their density, they're all related to their distance from the disk of the Milky Way. So finding these properties, and in particular the distance, is really, really important if we want to understand these gas clouds in the CGM of the galaxy. But finding distances is a really, really difficult task. There are direct and indirect ways of doing this. Direct ways involve finding the distance to a star that was formed within the high velocity cloud. This rarely happens though because the gas is really diffuse. So most people try to find a star that is along your line of sight. And then this way you know that the cloud is, this way you know that the cloud is closer than the distance of the star. Alternatively, if the high velocity cloud is interacting with the gas in the disk, we can use the information we have about the rotation of the galaxy to derive a distance to the high velocity cloud. And then for indirect methods, we can use models that are constrained using these observations, using these directly measured distances. Because these models were calibrated using these distances, we can use them to tell us about the ionizing radiation from the Milky Way disk as a function of distance. So here I'm showing the ionizing radiation from the Milky Way and its two largest satellite galaxies, the Large and Small Magellanic Clouds, and the sun is plotted in yellow for reference. The ionizing light is strongest closest to the center of these galaxies, so that's the region in red. And then as you go further out, the ionizing radiation decreases in intensity. So those are the blue and then the green regions. So how exactly do we use this indirect method to find the distance to a high velocity cloud? This is the whole point of my paper. So to begin with, we take advantage of what we know about the physics of photoionization or ionization by light. First, ultraviolet light from the Milky Way and the satellite galaxies hit the high velocity cloud. This causes electrons within them to move to higher energy levels or even to be completely removed or ionized. Now HBCs are fluid, so there's always the possibility that some parts of the gas cloud could cool down, and then you have the possibility of recombination. So you have the possibility that the electrons would recombine down to their original energy levels. Now, whenever an electron moves from the n=3 energy level to the n=2 energy level, a photon is emitted at 656 nanometers, and we call this line the H-alpha line. So we can use H-alpha as a tracer of ionized gas. But more importantly, because the emission of H-alpha depends on the high energy UV light, the intensity of the H-alpha that we observed is directly related to the amount of ionizing light of the galaxy. So in my paper, we use this method that I just described to derive the distance to one HVC in this whole plethora of HVCs in the Milky Way CGM. It's called the leading arm, and it's part of a group of clouds that were ejected from two of the largest satellites in the Milky Way, which I described before, the Large and Small Magellanic Clouds. This simulation here is showing LMC and SMC analogs, and it's just showing how that interaction between them causes gas to be spewed out of them and into the CGM. And this is what has formed structures like the leading arm here. So what did we actually do in this paper? We observed the leading arm with the Wisconsin H-alpha MAPA telescope in Chile. This is what the actual data looks like for one of our observations. We take those observed H-alpha intensities. And again, because the emission of H-alpha depends on the high energy ultraviolet light that is escaping from the galaxy, the amount of the intensity of the H-alpha will be directly proportional to this amount of ionizing radiation. And so we can convert these observed H-alpha intensities to ionizing flux or ionizing radiation, and then into distances. So this is in a nutshell what we did in my paper. And just to wrap things up, remember the properties of high velocity clouds depend on determining distances. And so in the future, other people can take new distances and then use them to derive things like mass inflow rate. So at what rate would the gas in the leading arm and in other parts of the Magellanic system, so the other gas structures that were ejected from the Large and Small Magellanic Clouds, at what rate would they be accreted onto the Milky Way should that happen in the future? So that's it, and I will take any questions.
All right, thank you, Jacqueline. I don't believe there are any questions in the chat, but someone did offer you a space ruler to help you measure the distances to the high velocity clouds.
You know, I wish they had given this to me like 4 years ago, you know, that made my life so much easier.
Science. Oh. Well, thank you, Jacqueline, and congratulations again.
Thank you.
A reminder that trivia and donation links to us and the Grand Stafford, our usual venue, are in the description.
All right, so next we have a segment called Astronomy in the News, which will be led by Dark Matter Dude. And so take us away, Dark Matter Dude.
Yeah, okay. So here we go. Okay, cool. So we're going to talk about what happened in the news this month, May 2020. It was kind of a light month, kind of just subjectively speaking. So we only have 2 stories for you, but let's get into them. So we have a black hole in our backyard that we just discovered. It is the closest black hole that we know about now. And I'm going to talk a little bit about how we found it. So there was this binary star, HR 6819. So it was 2 B-type stars. So they're pretty bright and very blue. And they were very close together, and everybody thought that they were in a binary. So some astronomers took some data, basically. They took spectra, so pointed a telescope, collected a whole bunch of starlight, scattered that light, and measured how much light they were getting in different wavelengths. And from that, they could figure out the movements of the stars. And what they found was that one of the stars in the binary was barely moving, and the other had about a 40-day period. So it was moving back and forth with about a 40-day period. And that's weird if these stars are both in a binary. And so what astronomers, what these folks figured out was it's actually a trinary system where the third star is a black hole. And they figured out the configuration. It's a black hole and a star orbiting around each other. And then the second star is further away, orbiting the entire system. And so that makes this, like we have found we know about a lot of black holes in our own galaxy. We know about one that's very massive in the center, but this is one of the closest black holes that we know about. So that's really cool. Okay, aliens. Cool. We're just gonna dive into this. Okay, so the Department of Defense, and this barely made the news, so this was wild to me. The Department of Defense recently declassified and released 3 official videos. One was taken in 2005, 2 others were taken in 2015. They all look pretty similar. They look, there's a screenshot of one of these on the right here. And they're like blobs moving weirdly. And in 2 of them, there's audio and the pilots are swearing, because what else do you do when there's something moving weirdly next to you and you're in a plane? But so the official language that came out in this press release was these were aerial phenomena, and they remain characterized as unidentified, which is the U in unidentified flying object or UFO. Now, so these are UFOs. We don't quite know what they are, or at least we didn't when the Defense Department released these videos. But they're probably not aliens. And there's a lot of explanations that go into this. There's a specific website, I forget the name right now, that basically just people watch these videos very intensely and figure out an explanation that isn't aliens. And so this could be rotating camera angles. So if you have a plane that's rotating and you also have a camera that's rotating to follow this object, that can produce some weird effects and make things look weird, like they're moving weird when really they're moving normally. You can have image artifacts. So if you have a really bright thing in a lot of dim light behind it, it can create weird spikes and diffraction patterns, and astronomers have to deal with that all the time when we're taking images. And it could also be this thing called parallax. So if you hold your finger out and alternate blinking your eyes, one eye open, then the other one, your finger moves relative to the background. That's a visual effect. It's very good for measuring distances, but it can also make some weird things happening. So a combination of these effects can actually explain all of these videos. Finally, just to emphasize this once again, it's not aliens, I promise. Okay. The last thing, I just thought this was super cool. Was this came out today, like this picture showed up on my Twitter feed today. Some astronomers took basically a really high resolution picture of a dust disk around a star, and the image on the left looks like it should be like a simulation or an artist image. It's real. It's 100% just a real data that this is the picture that they took. And so the cool thing is that if you zoom in on this in the left, where that white circle is in the center, that kink in that sort of spiral arm structure is a planet forming. We are seeing a planet form in real time. That's amazing. So yeah, I just wanted to share these. These are just kind of cool images. Yeah, that's it. That was what was in the news this month.
All right, thank you, Dark Matter Dude. So next we have our final speaker of the night. This is the Space Ventura Galaxy Detective, who is a professor of esteem at Texas A&M University in the astronomy department. Please take it away. Oh, actually, first I have a question for you. What was your dream job when you were a kid? Like thinking of, when you were growing up, what was your dream job?
Yes, thank you, Carbon Queen. Unfortunately, I think my dream job was exactly like our previous speaker, Jasleen's, which was astronomer. So I grew up with the original Cosmos documentaries by the Carl Sagan, and I believe I was hooked at that point. And I remember Jasleen, taking a book with me that had a picture of Betelgeuse, one of the largest supergiants nearby in the constellation Orion, next to a picture of our sun. And I was just struck at that point that the size difference was so great. So by age 8, I pretty much knew what I wanted to do, and I've been lucky they keep letting me do it. So
That's
I love this.
fantastic.
Yeah.
All right, well, please take it away.
Okay, well, thanks. And for everyone listening at home, having had to sit through really fun talks the last 50 minutes while drinking a beer makes this could be possibly a more lively talk than it normally would be. So if you'll give me a second, I'm going to get everything going here. We'll start sharing my screen as I steal the navigation. Oh, wrong screen. Okay. I hope you can all see this. So somebody give me a big shout out if they can't. Nevertheless, it's nice to get the invitation to come. This is unusual times, but we get to talk about astronomy, which, as I was once told by a mentor, if you're not doing it right, if you're not having fun, you're not doing it correctly. And the organizer said, this is the year, and in fact, almost to the month, the 30th year anniversary of the launch of the Hubble Space Telescope, which you can see depicted here. So it was launched quite literally 30 years ago on August 24th, 1990. So many of the former speakers who you are now listening to either were, I don't even want to consider their ages, but I suspect they were either very tiny or non-existent when the Hubble Space Telescope went up. And so we've had an entire generation of astronomers who've grown up with an observatory in space that's produced some of the most iconic visuals and taught us so much about the universe that it's beyond comprehension what our life would be like without the Hubble Space Telescope today. And so I want to start off with a tribute, and I'll even raise my glass as a toast to the Hubble Space Telescope, since it's brought so much science enthusiasm and deepened our understanding of the universe and all the phenomena that's in it. That was a good excuse to wet my whistle. Okay, but let's move on with it. So here is the Hubble Space Telescope. It has, since it's been operating for 30 years, it has produced so much science. I cannot possibly begin to cover it all in the limited amount of time we have. And even while trying to put together this talk, I realized there's no way I'm going to do it justice. It has produced some of the most iconic images we know. It has studied things like the planets that Jasleen told us about in the very first talk. This is with Jupiter, observed now without its great red spot. It's unfortunately on the other side of its orbit at the revolution at the moment. It has studied things like nearby star-forming regions. This is an extremely iconic picture, one of the first from the Hubble Space Telescope to make it above the fold in the New York Times. It's showing young stars forming within their birth clouds, and it's called the Pillars of Creation. It's in the Eagle Nebula, object number M16, if there are astronomers out there who would like to know what that is. It studied things farther away, such as nearby galaxies. This is a nearby galaxy M100, a very iconic galaxy, a spiral galaxy that is possibly similar to our own. This is heavily pasted together in different combinations of colors, so you can see the differences in the spiral arms and the core and the nucleus. It has studied collections of galaxies. This is a cluster of galaxies where each of the large yellow objects you see may be 10 times the size of our own Milky Way galaxy. And their combined gravity is so strong, and there's so much mass, that they actually act like a gravitational lens and bend and magnify the light of the objects behind it along our line of sight. And that's what you see as those snake-like, worm-like objects in the image, those long arcs that you see. It's a prediction from general relativity, from Einstein, that this should occur. And everywhere Hubble looks at these sorts of large concentrations of galaxies, it's able to see them. And then these provide tests not only for dark matter, but also for general relativity itself. And so Hubble's allowed us to study all of these kinds of objects, and I can't possibly go into all of it. I just have to save that for a future talk. Instead, what I really plan to do is just focus on a few of the things, or really one thing in particular, which is the idea that Hubble has peered deeper into the universe than any other telescope we've ever had. It's given us this knowledge of what the universe was like at extremely early times, and it's allowed us a chance to build up a picture of how galaxies might form and how the universe itself has changed over time. I'm going to focus on that mostly today. All right, but I feel obligated, since it is Hubble's 30th birthday, to give some history, especially for the youngins here who may or may not remember this or have been alive. So it begins, well, the history was long before the launch of the Hubble Space Telescope. For decades, maybe 40 years prior, people have been discussing the possibility of a space-based telescope. In fact, that's interesting because at the time, there were no digital cameras available back in the 1950s and 60s. Instead, they were considering putting photographic plates on a space-based telescope, and then they would drop them and parachute them back to Earth. The discovery of digital cameras changed that to our advantage. Nevertheless, this is a picture, I think the last picture of the Hubble Space Telescope on the ground. It's actually in the cargo bay of Space Shuttle Discovery there, moments before launch. After launch, the world was astonished when it began producing incredible pictures. As you may already know, the fact that the Hubble Space Telescope sits above the Earth's atmosphere allows it to be free of the turbulence that plagues all other telescopes. And as a result, the image quality, the angular resolution that the Hubble Space Telescope can see is beyond compare, even today. Even though it's a relatively small telescope in terms of diameter compared to the behemoths we have on the ground, it still produces some of the sharpest image quality we can imagine without the assistance of a lot of complicated technology that I won't have time to go into. But the Hubble can handle this. And so Hubble released, or NASA released, this first image. This is of a star cluster in the constellation open cluster NGC 3532. It was intentionally chosen because of that object near the top of these images, where the image on the left, I think you can see my mouse cursor, shows a ground-based image of the same field compared to the Hubble Space Telescope image. This is the first image released by NASA. And the goal was, they suspected this was a binary star. And in fact, Hubble can show you there are two individual stars. This was to capture the ability of Hubble to resolve these structures. It's just like seeing with sharper optics that produce this image. Now, at the time, scientists were already concerned that the image wasn't as good as they expected. If you sit down and calculate from an optics point of view, how sharp should the images be, they should be quite a bit better than what NASA had released. And NASA felt assured. They said, we're still testing it, we're still shaking it down, we're still letting the telescope breathe, we're still focusing the telescope. It's taking some time to get to that final image and to obtain the final image quality. Well, many of you probably know that wasn't what happened. In fact, additional tests showed that the image quality was not getting better. And by June 1990, NASA had informed everyone that yes, there was a flaw in Hubble's primary mirror that went undetected previously on the ground-based tests. And the outer part of the mirror was ground too flat by 4 millionths of a meter. And that's equivalent to 1/50th the thickness of a human hair. So barely noticeable in tests, but clearly large enough that it was not allowing Hubble the resolution that it needed or that was hoped to get. Well, nevertheless, Hubble was still superior to any telescope we had on the ground. It was producing an incredible range of good science then, but I have to skip ahead 3 years just because I'm limited by the amount of time I have. And in 1993, NASA undertook the first servicing mission to the Hubble Space Telescope using the Space Shuttle Endeavour, where during 5 spacewalks, it took 10 days, 11 days, the astronauts serviced the telescope. They took out 2 instruments, 2 of the cameras that were already outdated at the time, and they installed a new optic system called COSTAR. This optical system is basically like putting on glasses, if anyone of you have done that before, including myself, where suddenly you can correct the abnormalities in the mirror and allow Hubble the full image quality. And they kept it on there actually quite until a bit later. I'll explain what happened when they took it off and why. And so they installed this new COSTAR image. They began to test drive the new Hubble Space Telescope. This is an image of that same galaxy I showed previously on the second slide, M100, spiral galaxy, very much like our own Milky Way. This is the image from the original wide field planetary camera that the Hubble Space Telescope had. And you can see it's better than anything that was available from the ground, but not as good as you imagine Hubble Space Telescope images can be. After they did the optic correction, this is what it looked like. The image quality improved dramatically. suddenly you can see details in the galaxy that were unavailable before, individual star clusters. You can see the features in these dark dust lanes that or gas blocking starlight from behind them. You can resolve the nucleus and see what's going on within there. All of a sudden, everything became clear. And this allowed Hubble really into a golden age of science. I want to pause for a second and talk about what we actually learned from these things. So this is a compilation of Hubble images of the galaxy NGC 3982. I chose this one because it actually looks, we think, a lot like the Milky Way galaxy. This is very much like the images that Jasleen showed, what we think the Milky Way looks like. It has a central bulge. You can see that there, a very smooth yellowish orange feature in the center. And it's surrounded by what we call flocculent spiral arms, those blue lighted glowing features that move out from the galaxy. And then it's riddled with white light in there and these dark black regions. And those black regions are gas clouds that block the light of stars behind them. And it's from those gas clouds which new stars are able to form. One bit of evidence that we know stars can form out there because they have a large gas supply. Now the colors in this image, these are all from the Hubble Space Telescope, and we get this amazing image quality because of the optics on Hubble. But the colors in this galaxy tell us something about the nature of the stars in those areas. So we can begin, for example, with the blue-white regions out in the spiral arms. Those indicate the presence of very massive stars, some like that Jasleen showed before. They're much more massive and much more luminous than our own sun. As a result, they burn out very quickly. They're very short-lived. And these are all astronomical timescales we're talking about. But a star like those, these white blue, that produce this white blue light, they may only live for 10 million years or 100 million years. And if you imagine how long it took humans to evolve on the Earth, you would be hard pressed to find intelligent life around a star like that. There simply is not enough time for the evolution to occur. They're very short-lived stars. In comparison, so those stars only live for, those massive short-lived stars only live for 10, 100 million years. In comparison, our own sun has been happily chugging away for 4 billion years, 4.5 billion years, and will continue to do so for another 4 billion years before things really get bad. So these regions out there, these blue-white regions, indicate the existence of these short-lived stars. And we know that means that stars are forming there simply because there isn't enough time for those stars to move away far from their birth clouds before they die. They end their life cycle. And so that blue-white light indicates the presence of ongoing stars in formation. That's out in the spiral arms. If you look in the center, in the nucleus, you notice the color change. It's a yellowish, orange-ish color. And those stars that exist there are very much like our own sun. These are the longer-lived stars that have formed long in the past. And we know there isn't any star formation going on in the core simply because we don't see any of this blue-white light that we otherwise might expect if there were stars forming. So there's no stars forming there because we don't see any blue-white light. But we do see stars forming out in the spiral arms. Another indication that stars are forming out the spiral arms, and you may have already noticed this or asked the question, what is the red light you see out in the spiral arms? Well, those are massive short-lived stars still forming within their birth clouds. Those clouds absorb much of the blue light and only allow the red light to escape. And it's because those stars are so luminous that we can see them at all. And so again, that red light is indicating they're deeply embedded, obscured, newly formed stars. The white-blue light shows us where stars recently formed, and then the yellow-orange light shows us where stars formed long ago in the past. But then this tells us something. This tells us this galaxy like this formed most of the core mass in the very distant past, billions of years ago. It's still forming stars in the spiral arm, in the disk, and that's been relatively recent. But then we're getting this picture that this galaxy has been forming stars for billions of years, and the star formation is propagating slowly outward. I'll begin to get that picture. I'm going to have a drink to that. Okay, this is just a small tidbit of the science that we can get with the Hubble Space Telescope, but I want to use that as an orientation because everywhere that Hubble looks, it sees galaxies like this. Jasleen showed in her very first talk the small blank patch of sky that Hubble imaged produced an enormous number of galaxies in them. Everywhere we look, our sight line runs into a galaxy. This was seen early on, even with Hubble. This is 1993. After the upgrade to Hubble, the optics are all improved. Every time Hubble took an image, astronomers were agog that they could see in the background little blips of galaxies. Small, yes. Faint, yes. But they all had a unique feature that they were blue. By and large, the majority of the faint galaxies Hubble was seeing, even in 1993, were blue. And this, well, is surprising, maybe not in hindsight, but at the time it really was. Why would it be that all faint galaxies would be blue? And for your benefit, I'm going to zoom in here. It'll catch up in a second, just so you can see what I'm talking about. There are many galaxies in this image. Some of them are fully formed. They have yellowish red colors. And then as we go deeper into the image, the smudges you see are by and large very blue. And understanding now something about colors of galaxies, telling us something about their stars, this indicates that these galaxies, the light from them is dominated by these short-lived massive stellar populations. So this began a trend that was seen in Hubble, which was, how do we begin to understand this? Well, one of the things we needed to know were the distances to these galaxies. One of the realizations people had, and they've had for a long time, is that the distance is related to how fast the galaxies are moving away from us. So in this case, you can measure, and we can do this very accurately while using techniques both from Hubble Space Telescope itself and from ground-based telescopes, how fast the galaxies are receding away from us, their velocity away from us. It produces a Doppler shift that we can measure, and then we can use that to determine their recessional velocity. It's something we call a redshift, because as they move away from us, their velocity causes a reddening of their light, which we see as their Doppler shift, and we measure that as a redshift. So the redshift is the velocity at which they move away from us. And I don't have time to go into it, but one of Edwin Hubble, the astronomer's contributions to society, was he measured a relation between this velocity, how fast are galaxies moving away from us, and their distance, and showed they're correlated, which means the faster a galaxy is moving away from us, that is, how large its redshift is correlated with its distance. And the higher the redshift, the farther away the galaxy is. And now we can use this information. Jasleen was already talking about this before. The whole point here is that the galaxies are so far away. In this image, they may be billions of light years away from us. Well, the speed of light is fast, but it's finite. And so even though it's so fast, because of the enormous distances to these galaxies, it takes so much time to get to us. If a galaxy is 1 billion light years away, then it literally takes 1 billion years for the light to get to us. And I'm using literally correctly for all you people out there who may have heard it too many times while staying at home. The speed of light is fast but finite. So we're seeing galaxies not as they look now, but as they look when the light left them. And so galaxies that are 100 million light years away, well, we see what they looked like 100 million years ago. And galaxies that are 1 billion light years away, well, we see what they looked like 1 billion years ago. And galaxies that are 10 billion years away, we see what they looked like 10 billion years in the past. And so this allows us to build up a picture of what galaxies have looked like over the entire range of cosmic time that we see. Okay, just to summarize that. So we can measure a galaxy's redshift, which is how fast it's moving away from us. That allows us to determine its distance, and that allows us to see what the galaxies were like and measure their characteristics when the universe was much, much younger. Okay, this is a precursor. Well, let's go back to the Hubble Space Telescope and this milestone. So because astronomers were finding so many of these blue faint galaxies in their Hubble images, the director of the Hubble Space Telescope Science Institute, a man named Bob Williams, decided that he was going to devote an enormous amount of Hubble time, more than I think had been given to any other program at the time, 10 contiguous days to stare at one blank field of sky. And in fact, they chose that blank field such that the Hubble, during its orbit, would always be able to point at it, and the Earth would never get in the way. Something called the continuous viewing zone of the Hubble Space Telescope. That way they could maximize the amount of time compared to other programs that it might undertake. And when it did that, it saw the following. This is the first deep field that the Hubble Space Telescope acquired. It's called, not coincidentally, the Hubble Deep Field, or appropriately. It was, as I said, a collection of 10 contiguous days of imaging across a range of wavelengths, So you can see galaxies in all these different details. And we'll zoom in. And so what we'll see is, we can measure the distances to these using their redshifts. And we find that some galaxies look relatively fully formed. They have mature morphological structures. They have reddish light. And then other ones in the background, you might say, oh, they've got white, bluer light. They're just forming their stars, and they have very disheveled, irregular morphologies. So we're beginning to see something here. And then you have galaxies like these, which look very smooth and symmetric, and they're dominated by this orange yellowish light, which means they formed most of their stars in even the more distant past. Even though we're seeing them as they were billions of years ago, they must have finished forming their stars billions of years before that. And so this began to really drive home this idea that the universe is changing and that we can see galaxy evolution simply by looking at different epochs in the universe and putting it together, like strata in the Earth. As you go deeper, you see older geological features. Here, as we go deeper, more distant into the universe, we see what it was like at earlier times. So that was 1995, the Hubble Deep Field. And it really changed everything. So in 1997, Hubble had an additional servicing mission where one of the things they did was install an infrared imager that allowed Hubble to extend its wavelength coverage. And this was important because of this redshift, the fact that most of the features we want to see, especially where stars emit most of their light, was moving into the infrared. And we needed to be able to see that because the redshift was shifting it into those wavelengths. This is one thing that the infrared capability gave to Hubble. In 2002, the Space Shuttle Columbia installed another upgrade to the main optical imaging camera. And this allowed the Hubble Ultra Deep Field that Jasleen showed before. And these are just some images that were then available from it. It's a much larger field of view and going deeper. This camera was more sensitive than the one that did the original Hubble Deep Field. In 2009, Hubble had its final servicing mission. This was interesting too. They removed the optical corrector that Hubble had because at this point, all the instruments had been upgraded and each instrument had its own optical correction capability. And so Hubble was operating at full capacity at this point. One of the other things they did here was upgrade Hubble with something called WFC3, which is the Wide Field Camera 3. It was the third generation instrument. It had incredibly sensitive infrared coverage, a successor to the previous instruments, and allowed Hubble to begin doing truly deep fields now in the infrared, where you can see the red-shifted light from galaxies and study the stellar populations they contain, understand their stars in more detail. This is one of the images it took. This is a false color image because now most of the light you're seeing in here is in the infrared. And Hubble began a campaign of deep surveys. This is an image from something called CANDELS, which was the Cosmic Assembly Near Infrared Deep Extragalactic Legacy Survey. It's a long acronym, but it was the largest allocation at the time of exposure time from Hubble given to any guest observing program, something I was allowed to participate in. It truly set the course of my career here. I'll give a little animation of it. This is an image of the sky with some well-known constellations indicated, such as Orion and Sirius, which is one of the stars Jasleen showed earlier on. And then some other constellations you may or may not know. There are some features like the Pleiades, which people can recognize and identify and go look at. And the spot where Hubble looked is right inside this, one of the spots. There were 5. One of the spots where Hubble looked is right between these crosshairs with this funny acronym that we used. We understood, and you don't need to. You'll notice there's nothing in that crosshair. That was intentional because we don't want one of these silly bright stars to get in the way and interfere with us. So instead, what we do is we observe in this blank patch of sky. And we're going to shift it up a little bit. And then we're going to move forward and dive into this field. And it takes a while to get where the Hubble Space Telescope can see. This is just labeling the constellations. Those are not actually in the night sky. But all of these are. So this is an animation created by one of the visual artists who works for NASA and the Hubble Space Telescope. And we're finally zooming all the way down to where Hubble can see. There are thousands of galaxies in this image. Again, you'll see the larger ones, many of them look fully formed, and they may have orangish yellow colors, which indicate their stars were formed in the past, and they've mostly ceased forming their stars. And then you'll see other galaxies that show interesting shapes, and they might have blue-white light, which indicates they're rapidly forming stars. And then you'll see things perhaps like this object over here, which looks like it recently has a been a collision between two galaxies, and we're able to study and understand how those affect the process of galaxy assembly and galaxy evolution. Okay, what can we learn from these? All right, Hubble is now able to take images of galaxies over a range of wavelengths. And this means we get an image of what the galaxy looks like at different wavelengths. So this is one image of a spiral galaxy at wavelengths about what you could see. It's a Hubble Space Telescope image. The galaxy is around 9 billion light years away. But Hubble sees this in great detail. You can see the spiral arms. You can see individual star forming regions in it. But this is just at one wavelength. If in fact, Hubble observes over a range of wavelengths. In terms of numbers, if you want to see them, they go from 300 nanometers, which is in the ultraviolet, all the way to 1600 nanometers, which is well into the infrared, past what you can see. In fact, the region you can see with your eye is about that. That's limited from blue light to red light. But then we have the blue light on the left, all the way to the red light on the right. Okay, what does this tell us? Well, we see the morphology, the structure of the galaxy change as a function of wavelength. Remember, the bluer light is telling us where new short-lived stars are, because they don't live long. If you see them, that's telling you they recently formed, and that's tracing where stars are forming now. So what the galaxy looks like in blue light tells us where the stars are forming now. And as we go to the redder, longer wavelengths, this is telling us where stars formed in the past. And so we're able to build up a picture where stars have already formed, and we can see their longer lived descendants, and where stars are forming now. They're short-lived, massive stars. And we build all this up in a picture. We can do the same, this is just one example, and we can make nice color composites. This is of the bluer light, so we can see where stars are forming now. This is of the redder light, this is where stars formed in the past. This is just one example. It's a very iconic type of spiral galaxy. You can see even a bulge and perhaps a bar in this galaxy, even though it existed. We're seeing it as it existed 9 billion years in the past. Other galaxies look more like this. This is a galaxy at the exact same distance from us. Here, we see no change in the structure, and the galaxy has the same appearance everywhere, which means the entire galaxy is forming stars at this moment, and it seems to be doing it in a very irregular, haphazard way. And it informs us about how galaxies form their stars, when they did it, and how fast they did it. And we can build up this whole picture. And there are two messages I want you to take away from this. The first one is the following, and I'll walk you through this. This is adding up all the light from all the stars that we see in all the galaxies in these Hubble deep fields. On the x-axis of this plot is this redshift quantity. This is how fast are the galaxies moving away from us. And we can measure it. We sit here at 0, and as we look to more distant galaxies, remember this is a measure of the distance, the galaxies are moving faster and faster and faster away from us. And if you have questions about that, you can ask it later. But we measure the redshift, and that tells us how far away they are from us. On the top axis, this is converting that redshift into billions of years ago, because if the galaxies are more distant from us, we're seeing them as they looked at this age. So here at redshift 0, well, that was 0 billion years ago. That's right now. And then as we go to higher redshift, larger redshift, like redshift of 1, well, we're seeing galaxies as they appeared 8 billion years in the past. And if we look at redshift of 4, then we're seeing how galaxies looked 12 billion years in the past. And it's not a linear scale up here. And again, that's because we have to fold in the effects of special relativity and all of this. And again, you have to come take my class at Texas A&M if you want to learn more about that. So we can trace now how fast galaxies were forming stars as a function of the age of the universe. On the y-axis, this is telling us how fast galaxies are forming their stars in a region of space. And so we can compare how fast galaxies are forming stars now to how fast were they forming stars in the past. So it's normalized so that 1 sits here. This is the now on this axis. And as we go into the past, we see that the universe is rapidly ramping up the amount of which galaxies are forming their stars. And by a redshift of 1, 8 billion years ago, galaxies are forming their stars at a rate about 10 times the present value. This seems to peak somewhere between 9 and 11 billion years ago. And this is the peak period of star formation in the universe. Galaxies were most active at forming their stars during this region. And then as we go to the exciting thing, as we go to even more distant galaxies, we see this begin to drop off again. And we're seeing these first generations of stars, because here, if you turn the clock and go from the Big Bang to the present, galaxies are rapidly ramping up their star formation at these times. And so to be able to measure this using these deep fields from the Hubble Space Telescope, how fast are galaxies forming their stars? And we've done it over almost 13 billion years of cosmic history. We just have another billion years to go, but that's the hardest one. Okay, the other piece we've been able to understand, this is the second thing we've been able to see, is understanding what the structures look like in these galaxies. This is a composite of what luminous galaxies, the brightest, most massive galaxies, look like nearby. If you just do an atlas of nearby bright galaxies, most of them have shapes you might recognize. There are elliptical galaxies, there are spiral galaxies, and they're very iconic, very beautiful in this regard. And by and large, 90% of luminous massive galaxies in the nearby universe are represented by either spiral galaxies or by ellipticals. Only a small fraction are in a class that are hard to classify in this way. They are exactly the ones, though, that we're interested in, because these are the ones that are forming their stars. They're dominated by this blue-white light. Whereas by the time you get to things like these smooth elliptical galaxies, well, they've got this orange yellowish light, which means they formed all those stars in the past. This is the local universe. As we shift to the more distant universe, the Hubble Space Telescope tells us that galaxies were much more irregular in their appearances. This is only 6 billion light years ago. There's much more history before that. And already we've seen that at this point, of the luminous galaxy population, only 30% are spirals, less than 20% are ellipticals. More than half fall in this class of irregulars and peculiars. And this seems to be a trend in the sense that as galaxies are most rapidly forming their stars, we're also seeing that they're assembling them into some new configuration. So the process of star formation is very messy. It's not orderly. And it seems to be a not smooth process. But over time, somehow galaxies become more mature. And I think this is a good analogy with age, where clearly growth in children is a very messy process, but then they mature and become the iconic, nice to look at individuals who are adults in the universe. Okay, where does the future go? Well, I'm going to gasp for some indulgence amongst my organizers, because I know I'm probably taking too much of your time. It's just my enthusiasm on it. But if you'll bear with me, we'll see what we have. Well, one of the things is the following. Some work we did recently using all these Hubble data was put together a picture book of how galaxies like the Milky Way would have formed. This is a plot of galaxies, linking them together, where we know how many stars they have and how fast are they forming those stars. And so we can begin to find images like that in our data, in our Hubble Space Telescope data, and put together a picture of how they formed. This is what we think a Milky Way type galaxy would have looked like between 9 billion years in the past and 12.5 billion years in the past. And at that point, the Hubble Space Telescope is no longer able to detect them. They're all at the same relative scale. So this is the same physical size as this image, as this image, as this image. And we're seeing this bulge form up in the centroid of a galaxy. And the mass has increased by a factor of 10. This is very much like a child growth phase, where everyone who has children knows they start off eating constantly and they double and triple, quadruple their weight. And my teenager has just gone through an enormous growth spurt. And we're having trouble finding clothes for him, since it's hard to take him to retail places to get new clothes at the moment. Okay, but then what happens here? Well, we can go forward with Hubble, and we see that over time, the disk develops, we find spiral arms, and we begin to put together a picture of how a galaxy like the Milky Way formed. Well, what's wrong with this? This is all we've done with the Hubble Space Telescope. What's wrong with this picture? Well, one is, this is just one track, one possible evolution. We're limited by statistics. Even though we have thousands of galaxies, we really need more like millions to understand at every single epoch in the universe how galaxies like the Milky Way are assembling. So we just need more data. The other thing we realized is, well, we're looking at a picture of a baby Milky Way as it appeared 12.5 billion years ago. But at that point, it already contained 1 billion stars. At present, it might have 100 billion. But 1 billion is still a lot. Jasleen showed us a nice image of how the comparison between one solar mass and a 1 billion solar mass black hole looks. 1 billion is quite a bit, as you might imagine. What happened before this? Well, the successors to Hubble, there are 2 of them I'll mention briefly at the end of this presentation. The first one was called the WFIRST, which is the Wide Field Infrared Space Telescope. It was recently renamed, very recently, meaning today, it has been renamed the Nancy Grace Roman Telescope. Nancy Grace has been deemed the mother of Hubble. She was a scientist and NASA administrator who shepherded not only the Hubble Space Telescope, but many of the other space observatories through NASA to success. And so it is to her credit that her legacy will live on as having her name sake of this telescope. So from this point on, it will be the Roman Space Telescope. WFIRST has been renamed as of today. And here's a nice press release that NASA put on their website today. Why is WFIRST so important? Well, it has a similar size to the Hubble Space Telescope for its mirror, but it's much more compact. It was donated to NASA by something called the National Reconnaissance Office, and I don't think they can hear this presentation, so hopefully they won't care that I said that. We'll talk about that later if you want. But what can it do? Because it's more compact, it can see a much wider field of view. That white square is what the Hubble Space Telescope can see with its field of view. The blue polygon is what the Roman Space Telescope will be able to see. It's a factor of almost 200 times the field of view. And so in terms of just sheer statistics, it would take 200 Hubble images to equal 1 of these Roman Space Telescope images. And so we'll no longer have the statistics problem. We'll be able to do as much with that as we want. The other telescope I'll mention, many of you are probably familiar with, is the James Webb Space Telescope. This is, as of today, still scheduled to launch in March 2021. It is another true successor to Hubble in that it's just much larger. The mirror you see here is almost two and a half times the diameter of the Hubble. It has to unfold on its way to L2, which is an artificial gravity point that away from the Earth. That is good because the Earth itself is an enormous source of background for Hubble. The disadvantage is we can't go out there to fix it if something goes wrong. And there are a lot of moving parts as you're seeing them unfold here. So what you've watched so far is the sun shield deploy. That is to protect James Webb from the radiation from the sun and to also keep heat down and to keep it very cold. The telescope is designed to operate in the infrared. That was the secondary deploying out in front, and then the primary unfolds. Just to put this in perspective, this is an image to scale between the Hubble Space Telescope on the left and the James Webb Space Telescope on the right. Down below, you see a size comparison of the mirrors relative to some human, and they're to scale. So the size of the mirror of the James Webb is more than twice the diameter of the Hubble Space Telescope. The James Webb is also optimized to work in the infrared, and this is because all those features that we need to study in these distant objects that James Webb might find will be redshifted into that part of the electromagnetic spectrum. And so James Webb is optimized to work there. And it should be allow us to trace the very formation stages of galaxies like the Milky Way, perhaps all the way back to the Big Bang itself. Okay, with that, I'm going to end. I'm going to end just here with a quote from Edwin Hubble that I always find very inspiring, which says the following. It's from his book, The Realm of the Nebula, published in 1936. It says, eventually we reach the utmost limits of our telescopes. The search will continue. Not until the empirical resources are exhausted need we pass on to the dreamy realms of speculation. And I think that encapsulates both what we've learned from the deep fields of the Hubble Space Telescope and what we will learn from these future telescopes that we'll see soon. So I'll stop there. Happy to take any questions.
All right, thank you, Space Ventura. We'll do one question right now, and then after trivia answers, we'll go through a few more questions that we have. So for now, the first question is from Snoop Jedi, and it is there a place in the future for more spectrum-spanning telescopes in space like Hubble, or are telescopes with greater wavelength specificity more useful?
I'm sorry, I something triggered in the sound just as I was trying to say that. I don't know if there's internet or not. Could you repeat
You're fine.
the question?
So I think essentially it's, is there a place in the future for space telescopes like Hubble that cover a very broad wavelength range? Or do you think it's going to be more like, the James Webb Space Telescope where there's a finite wavelength range and they're really focused?
That is an excellent question. So of course, it all comes down to, unfortunately, money and how much money you're willing to invest in a telescope. It also comes down to the fact that these different wavelengths of light require different technology to detect, and you can do that at different efficiency. And so many telescopes will be able to observe large portions of the electromagnetic spectrum. James Webb will actually observe from 1,000 nanometers all the way to 20,000 nanometers, but it does that with 2 different main cameras. And that comes down to how much money do you have and how much space do you have on the telescope for the multiple technology. NASA certainly is aware of this, and they also know that when they launch something into space, there's a huge cost associated with that, and they want to maximize what they can do with it. And so they always run trade studies to determine exactly the answer to that question, which is how much can we do with what we have and do it well? A telescope that's optimized for the infrared, like James Webb, should just focus on the infrared. And then there are actually plans in the works. There are telescope designs on the market to observe, for example, in the ultraviolet. So I think there's a combination of both. They want to maximize how much wavelength they can coverage, but then also they have to understand that certain telescopes will just simply be optimized. So I think you'll see a that's not really answering your question, I feel like.
It's very thorough.
But you're going to see you'll see a balance between the two.
Yeah. No, thank you. That's great. Yeah. All right. Well, so we'll have more questions for you after we go over the trivia answers, and we'll bring both back on at that point. But thank you.
Okay, gonna hop straight into trivia, which this month was at the speed of light. So if you were traveling at the speed of light, how long would it take you to reach the following objects? All right, first up, the sun, fairly close by at about 8 minutes. Next, the moon, even closer at a second. Third, Mars, we're moving out now. That would be about 3 minutes from Earth, most times of the Earth year and the Martian year. Fourth, Pluto. We're starting to get a lot further now. It would take you 5 hours to get to Pluto if you were traveling at the speed of light. Next, Voyager 1, the furthest human-made thing that we've sent out of Earth as of 18th May. It would take you 20.5 hours to get there at the speed of light. Question 6, the Alpha Centauri system, or Object 6, that would be 4 years. And it's really a triple star system that we're talking about, not just one star. Next up, Sirius, the brightest star in the sky, at least from the Earth's perspective. It would take you 9 years to get to Sirius. Next, Sagittarius A star, the black hole at the center of our galaxy. From Earth, it would take you about 26,000 years to get there. Nothing to sneeze at. 9, the Andromeda Galaxy, and we can see that lovely image that Jasleen showed us in her talk. To get to the Andromeda Galaxy, you would have to travel about 2.5 million years at the speed of light. Last up, the edge of the observable universe, the furthest we can possibly see right now, given that light travels at a finite speed. To get to the edge of the observable universe, you would need to travel for 46 billion years, still moving at the speed of light, the fastest you could go. So we will let our trivia winners know if they've won and somehow communicate a way to get your prizes to you. But yeah, if you took part, thank you for taking part.
That's great. All right, so really quickly, I guess we'll bring back our 2 speakers and ask whatever leftover questions that we have. All right, so for Space Ventura, we have one more question from Felix Martinez. Would the blue polygon shape, would W first have a lower resolution than Hubble?
That's a really good question. So the answer is actually no. It should be about the same as Hubble. There will be some distortions across the field, but they can use optics to take most of that out. So it really will produce very similar to Hubble type image quality, just over a field of view that's 180 times the size. That's why it's such a monster.
That's great. I have another question from Jonathan Cohn. Bear with me, it's kind of a joke. So you said that Hubble is 30, but I thought it was between 67 and 74. It's really bad. Hubble joke. Okay, it's fine. Anyway.
Tell John we will talk offline.
All right, and final question for you, Space Ventura. What is your favorite redshift?
Oh, my favorite redshift? Unfortunately, I am easily distracted by anything that interests me, and objects are at all different kinds of redshifts. I think if you were to ask me right now what redshift I'm most excited by, it's going to be the ones we haven't seen yet with the Hubble Space Telescope. We know the galaxies have to be there. Like I said, the earliest stages of the Milky Way we can see, which are around redshift of 3, they already contain 1 billion stars. Well, I want to see what happened before that. And that means we need to move to even higher redshifts. That is the era of the James Webb Space Telescope.
Knock on wood.
Okay.
It's going to go up. It'll be great. All right. NCM33, do you have any questions?
I do see another question for Space Ventura. If we're talking manned missions to the moon, would a telescope there do for astronomy purposes?
Oh, that is a great question that would actually cause some consternation between different astronomers. There are people who think absolutely we should be building telescopes on the moon simply because there's no atmosphere. You can observe most of the time. And they're also talking about radio telescopes on the moon because then you could observe on the far side of the moon and use the Earth to block all this annoying cell phone interference we have on the Earth side of the moon, for example. Again, I think it just comes down to cost. I think if given infinite amount of money, we would love to see telescopes on the moon, but then someone has to maintain them. You have to find graduate students to go there. I know a few who probably would if we gave them the option.
Absolutely.
Okay. So, but I think I would love to see that there. People talk about the pros and cons. It's a little difficult to operate in space, as the space observatories have demonstrated. But one day, maybe in the far future, we will see that.
All right. Well, thank you very much. All right. Well, as the final note, we'll be doing some closing announcements. Give this 1 second. All right. So just as a reminder, thank you everyone who did trivia. That was amazing. Like and subscribe to our YouTube page. You'll get updates on when we go live and all these fun things that we're doing. We have some other stuff planned, so stay tuned. And then also follow us on these social medias. Like we said before, we have Twitter, Instagram, Facebook, and then the overarching headquarters, astronomyontap.org, which has all the events from all the Astronomy on Taps around the world. Now, we normally host our in-person Astronomy on Taps at the Grand Stafford, which is an amazing venue, and the people there take care of us, and we love them. Normally, we tell you to tip your bartender in person, but because of right now, if you feel so generous, please feel free to tip your bartender through this Venmo app. This is the owner, Jose Quintana 20, and if you put Stafford Tip in the description, they'll know it comes from us. And then finally, if you want to support us and donate, we have 2 different donation cash apps right here. The tag for both of them is AoT BCS, and we have some AoT shirts left over. We'll take a donation of $15 for them. And our next event is June 17th, 2020. It's the 3rd Wednesday of June, as all our shows are, and please tune in. We'll be live again. All right, and thank you for everyone who put your questions in. That was awesome. So, thanks. Cut to the show.
This has been Astronomy on Tap, BCS Virtual Edition 2.
Yay. All right.
Have a good evening, everyone. Stay safe.